lengths of some of these segments that we draw in circles. We're not talking about arc measures anymore. Now we're talking about a physical length. And this is kind of a neat thing. This lesson actually has a famous name to it. It's called the power of a point. And yeah, we're going to do some algebra today. So let's talk about what we're going to be doing. So there's 3 different scenarios today. So you might want to stop and draw these in your notes. On the left, we have 2 intersecting chords. So we have chord AB and chord CD. That's these 2 chords here. And they intersect at point P. And I'm always going to call the intersection of these segments point P in this case. In our middle diagram, we have 2 secants. Remember, a secant is a segment that goes from a point and goes through a circle twice. So I want you to think of this as almost like 2 segments. There's segment PB, this long one, and there's also segment PA. There's like a shorter segment there. And the same thing on the bottom. There's segment PC. And then there's the whole segment, segment PD, that whole segment there. And then you have a secant and a tangent over here. So you have the tangent, which strikes the circle at 1 point only. And then again, you have the 2 segments. You have segment PC and then segment PD. So let's talk about the power of this point, the power of point P. So I'm going to go to this sketch that I made over here for a moment. So this has the 2 chords that are crossed. It's really similar to the diagram before. But what I want to point out to you is these measurements that you see over here on the left side. These measurements right in here. So this first thing talks about the distance from point P to point A. And the next one is point P to point B. And in this box here, this box labeled number 1, what I want you to notice is that when I multiply those 2 distances, whatever they are, I get 15.2136. And if I multiply the other distances from P to C and then from P to D, if I multiply those 2, I get the same measure. And here's the power of this point. No matter where I put the point inside this circle, those products, when you multiply those distances together, it's always the same, no matter where they go. And that's so cool. But wait, there's even more to it. Let's drag point P outside the circle. And look what happens to those distances. Now the distance is 53.2415, and the other one is exactly the same. This is pretty cool. And again, no matter where I put point P, those 2 products are always the same. And that's the power of this point. So when we talk about the power of point P, what we're saying each time is that the product of the segments that point P makes with the circle is always constant. So in this case, PA times PB is equal to PC times PD. I'll pause for a minute while you write that down. The rule is the same for the 2 secants. My green segment, PA, multiplied by the blue length, PB, is the same as the purple segment, PC, multiplied by the whole red segment, PD. The power of that point. Now, you might be looking at the secant and the tangent and saying, well, wait a minute, there's not really like 2 segments there. Here's the cool thing about it, is that think of PA as being like 2 segments in one. So it's really PA times PA equals PC times PD. And yeah, I'm going to simplify this a little bit and say if you square that tangent length, it equals PC times PD. So again, pause the video, take a moment, write this down, draw some pictures. This is the rule. It's the power of point P, that the product of the lengths of the segments from point P is a constant value. It's the same no matter what. So that's why we can make equations out of it. Okay, let's go and see how this thing works in action. Take a look at this diagram here, maybe draw this picture. We have a circle and 2 chords, P, Q, and RS, intersect at point T. So t in this case is the power point. I'm given some measurements. I'm asked to find st. Well, let's do the geometry. The power of the point says this is 10, q to t is 6, r to t is 15. I'm looking for the length of st. Let's call that x. So here's the geometry behind it. Point t is the power. So 10 times 6. If I multiply the distance from t to both p and q, it's going to equal the distances multiplied to r and to s, 15 times x. There you go. This is an equation you can solve. 10 times 6 is 60. When we divide both sides by 15, we get x equals 4, so the length of st is 4. Beautiful. Let's take a look at another one. Now we'll do two secants. I have two secants that are drawn from point P, so point P is that powerful point. Let's label our diagram. It says that PA is 5, CD is 6, AB is 3, and we want the length of PC. We're going to call PC's length x. Okay, here's what the power of the point says. The power of the point says, if I multiply this length PC times this length here, PD. Now hold on a second. Let's figure out how long PD is. It's some distance x, and then it's 6 more than that. So this whole distance is x plus 6. So in my equation, I'm going to write x times x plus 6. Oh, baby. This is looking like some fun. Take a look at the bottom one. Let's do the power of the point. It's equal to this segment, PA, times this length here, PB. PB's whole length is 8. Oh, I gotta write that in blue. So here's our equation, the power of the point. So when we start multiplying this out, yeah, we get 40 on the right side. We have to do our distributive property and get a quadratic equation. Oh, yay, we love it. So there's a lot of different ways to solve a quadratic equation. One of the ways that we'll stick to now is by setting it equal to 0 and factoring. So we'll subtract 40 over to the left side. So we get our quadratic equation, x squared plus 6x minus 40 equals 0. Now, you might remember how to factor from last year. A lot of their teachers like to use the a and the m method. It's got to add to that and multiply to that. So I'm thinking of things that multiply to 40. So 40 is usually like 8 times 5, 10 times 4, 20 times 2. But the pair's got to add up to 6. So the ones that are going to work are going to be 10 and 4. Now I also need things that multiply to x squared. So it's going to be x and x. Now you got to play with the signs for a minute to figure out how do you get a positive 6 from a 10 and a 4. Well, that's positive 10 minus 4. And congratulations, you just factored that. So when we solve this now, we set both of these factors equal to 0. And when you do that, you get two answers, x equals negative 10 and x equals positive 4. But wait a minute, we're talking about the length of a segment. Segment lengths can't be negative, so we'll reject that root. So the length of segment PC is equal to 4. All right, so the power of the point is the geometry. You might have to do some factoring to do the algebra. Hey, let's try another one here. Let's talk about a tangent and a secant. Maybe you want to try this one on your own. Pause the video if you're brave. All right, how'd it go? Let's see how you did. It looks like PB has a length of 4 and BA has a length of 12. PC is what I'm looking for. Let's call that x. So here's that special case where there's only one segment, segment PC. So we have to actually square it. So we have to do x times x, or x squared equals. Now the power of the point says it's this distance times the entire distance. That entire distance is 16. And here's the equation we want to solve. So 4 times 16 is 64. We solve this equation by square rooting. So if we take the square root of both sides, we're going to get that x equals the square root of 64. It has two answers. One of them is a positive 8, and one of them is a negative 8, because negative 8 squared is 64. But again, we got that negative length. Let's reject it. So the length of segment PC is 8. Okay, that's the power of a point, man. Good stuff. One last thing, though, here. Let's suppose we have two tangents. Well, what we know is that from before, if we take the length of PA, since there's only one, we kind of square it. So we do like PA squared. And then it's going to equal the square of PB. That's our power of a point. But we can just simplify this by taking the square root of both sides and getting that the two tangents have the same length. So PA and PB are the same. So these tangents are equal. That's a big one there. Let me show you how we're going to play with that. In this diagram, I've got this figure here. The circle is inscribed inside the triangle. So these are all tangents. So TG has a length of 20, GE has a length of 8, and RS has a length of 7. I got to find the whole perimeter. Well, watch this. Because tangents are the same length when drawn from the same point, since PA and PB are the same length here, if this segment RS is 7, RE is 7. If GE is 8, GI is 8. And if this whole length here was 20, 20 minus 8 is 12, so TS is also 12. And then when I add things around the perimeter, let's see, 12, 27, I think I get 54 as my perimeter when I add up all those sides. So that's the power of a point. It's really a cool thing to do.